I think people see the formulas for standard deviation and get a bit alarmed by the topic, but the actual concept of standard deviation is not that difficult in my opinion, okay? Let's consider these two data sets here. Now, if you look at them for a few seconds, hopefully you can appreciate that they are very different. They don't really have that much in common. However, completely by chance, they happen to have the same mean to two decimal places of 24.17. This notation here with the bar on top, this is the notation for mean. And this is kind of one of the problems with presenting the mean on its own without any context. It doesn't really give you the full picture of what's going on with the data, and it can make it look like these two data sets here are quite similar, even though they don't have that much in common. And this is where standard deviation comes in. It's given this notation here of sigma, and the standard deviation is defined as the average distance from the mean. It's not exactly this if we're getting very technical, but at A level you can just say this is what it is, okay? So for the first data set, this has a standard deviation of 1.95. We'll talk about in a moment how we can calculate this. And this is a small standard deviation. And this is because the distance from the mean and all of these data points here are very small. All of these data points are very close to the mean. Now, for the second data set, we have a much bigger standard deviation of 17.02. And this is because none of these data points here are really close to the mean. They are all very far away from it, and this gives a much bigger standard deviation. So when you combine the mean with the standard deviation, it gives you a fuller picture of what's going on in the data. Mean and standard deviation are a very good partnership. Mean is a measure of location. It tells you the average location of the points, and standard deviation is a measure of spread. It tells you how close the data points are to the mean and how spread out the data is. A small standard deviation means the data is very close together, and a large standard deviation means it's very spread out. Okay, now before I talk about how to calculate standard deviation, we have to start with how to calculate variance. Okay, so variance is given this notation here with sigma squared. Okay, now there are quite a few formulas given for variance in the textbook and in the formula booklet that make it seem more complicated. In my opinion, they all mean the same thing, they're just written in different ways. This here is the best formula for variance. Okay, so its variance is equal to sigma x squared. Now, annoyingly, this symbol here and this symbol here both mean sigma. This is uppercase sigma and this is lowercase sigma, okay? So it's sigma x squared over n minus sigma x over n squared, where x are the data points and n is the number of data points, okay? Now, a really nice way to remember this formula is it's the mean of the squares minus the square of the mean, and I think this is a brilliant way to explain it, okay? So this part here is the mean of the squares, because in the numerator here, sigma x squared means every data point we're going to square it and then we're going to add them all together, and then we're dividing it by n. So this is the mean of the squares, and then it's minus, and then this here, this sigma x over n is actually the mean, because sigma x means we're adding all the data points together and then we're dividing it by the number of data points. So this is the mean, and then we're squaring it, so this is the square of the mean. Okay, so this is the variance. Okay, we're going to go through an example in a moment to show how this actually works with data. Okay, and then the standard deviation is the square root of the variance. So overall, this is the formula for standard deviation. I've just square rooted both sides of this formula up here. Okay, I just want to mention a couple things to do with the variance. So this down here is another version of the formula where x bar is the mean of the data. So the way this formula actually works is every single data point, we're going to take away the mean and then square it, and we're going to do this for every single data point and then add all the values at the end and then divide it by n. Okay, now this version of the formula, we never use this. We always use this one up here because it's a lot easier to use with raw data, as we'll see in a moment. I just wanted to mention this formula here because it's mentioned in the textbook. Now, another way that we can write this formula is like this here, with this SXX, and this SXX is equal to this numerator here. This is essentially just a shorthand way of writing this formula here, okay? Now, this version of the formula, along with SXX, is given to you in the formula booklet. So if you do need it in an exam, you can just access it in the formula booklet, okay? Now, it is actually mentioned on the specification. You need to have an understanding of what this SXX actually means, okay? It's literally just a shorthand way of writing this numerator here. Now, they haven't asked an exam question on this yet, as far as I can see, but theoretically, they could ask you one because it's mentioned in the specification. They could ask you a question, for example, where they say that SXX is equal to 50 and you need to find the standard deviation, okay? The way that you would just do this is just plug this value in as SXX into this formula here, rearrange in order to find the variance, and then square root it in order to find the standard deviation, okay? As I said, it's in the formula booklet if you do need access to it. They ask a few questions about this in the mixed exercise 2 in the textbook, which may be good practice to have a go at. I'm not going to mention this again in this video though. Okay, so let's go through an example to show how this works. So we have this list of data here. This is actually the list of data that we talked about at the start of the video. And for part A, we need to calculate the mean. Okay, so remember the mean, which is given this notation here, is equal to the sum of all of the data values divided by the number of data values. Okay, so the sum of all the data values is 21 plus 23 plus 24 plus 24 plus 26 plus 27. And if you put this into your calculator, this is 145. And then n, so there are 1, 2, 3, 4, 5, 6 data values, so n is equal to 6. So therefore the mean is the sum of the data values, which is 145 divided by n, which is 6. And if you put this into your calculator, it's equal to 24.1667. I've given this to 4 decimal places because we're going to use this answer in part B to calculate the standard deviation, and if you're going to do that, I would recommend giving it quite a few decimal places so there's no risk of kind of any rounding errors when you're calculating the standard deviation. Okay, and then for part B, we need to calculate the standard deviation. Okay, so remember this here is the formula for variance. Okay, so in order to use this, we need to find the sigma x squared. So this is all of the data values squared and then added together. So sigma x squared is equal to 21 squared plus 23 squared plus 24 squared plus 24 squared plus 26 squared plus 27 squared. And if you put this into your calculator, this is equal to 3527. So therefore the variance is going to be this sigma x squared, which is 3527, divided by n, which is 6, and then minus this here. Now remember, this is the square of the mean. This sigma x over n is the mean, and in part A we figured out the mean to be 24.1667. So therefore we're going to square this here, and if you put this into your calculator, this is equal to 3.8039, and then it keeps going like this. So this is the variance. Remember, the standard deviation is the square root of the variance. So the square root of this 3.8039, etc. And if you put this into your calculator to 2 decimal places, it's 1.95. Okay, so rather than doing it for a list of data, it's more likely they'll ask you to do it for a frequency table. So here's an example of this, where we have the frequency table that shows the time in minutes it took for a group of runners to complete a race rounded to the nearest minute. And for part A, we need to calculate the mean. Okay, so we talked about how to calculate the mean for a frequency table in the measures of central tendency video. So remember, the mean is equal to the sum of all of the data values divided by the number of data values. So the sum of all the data values here, so we have 7, and this occurs once, and then we have 8, and this occurs 4 times, and then we have 9, and this occurs 11 times, and then we have 10, and this occurs 7 times, and then we have 11, and this occurs 3 times. And if you put this into your calculator, it's equal to 241. So this is the sum of all of the data values, and then n is the number of data values, so this is just going to be the sum of the frequencies here. So 1 plus 4 plus 11 plus 7 plus 3, which is equal to 26. Okay, so therefore the mean is equal to the sum of all the data values, which is 241, divided by n, which is 26, which if you put this into your calculator, is equal to 9.2692. Okay, and then for part B, we need to calculate the standard deviation. Okay, so this is the formula here for standard deviation. So firstly, we need to find sigma x squared. So this is all of the data values squared and added together. So sigma x squared is equal to, so we have 7, so it's going to be 7 squared, and this occurs once, and then we have 8, so it's 8 squared, and this occurs 4 times, and then we have 9, so it's 9 squared, and this occurs 11 times, and then we have 10, so it's 10 squared, and this occurs 7 times, and then we have 11, so it's 11 squared, and this occurs 3 times. And if you put this into your calculator, this is equal to 2259. So therefore the variance is equal to sigma x squared, which is 2259, over n, which we figured out in part A is 26, minus, and then this here is the mean, and we know the mean is 9.2692, so it's 9.2692, and that's the mean squared, and if you put this into your calculator, it's equal to 0.9665, and then so forth. So therefore the standard deviation is going to be the square root of this 0.9655, etc., which if you put this into your calculator to 2 decimal places is 0.98. So this is the standard deviation. Okay, now the most common question they will ask you is to estimate the standard deviation in a grouped frequency table. So here's an example of this. So we're told a delivery company delivers 34 parcels in one day, and the distribution of the parcel weights in kilograms is shown in the grouped frequency table below. So this is this table here, okay? I'm going to ignore this part for now. I'll come back to this in a moment. For part A, we need to estimate a value for the mean. Okay, so we talked about this in the measures of central tendency video, the video that I've already talked about. This is going to be an estimate because we do not know the exact values of the data points because they are grouped together in these intervals here. Okay, what we're going to do in order to make the estimate, we are going to find the midpoints of these intervals here. Okay, so the midpoint between 0 and 5 is 2.5, the midpoint between 5 and 10 is 7.5, the midpoint between 10 and 15 is 12.5, the midpoint between 15 and 20 is 17.5, and the midpoint between 20 and 25 is 22.5. And what we're going to do to make our estimate is we're going to assume that all of the data values are these midpoints here. Okay, so in order to do the mean, so we normally do x bar, but in this case, because we're talking about the weight and we're told this is W, therefore we're going to say that this is W, the data. So the mean is equal to the sum of all the data values added together, which in this case we'll say is W, and this is divided by n, which is the number of data points. Okay, so the sigma W here is all of the data points added together. So sigma W is going to be, so we have 2.5 here, and this occurs 11 times. Then we have 7.5 here, and this occurs 10 times, and then we have 12.5 here, and this occurs 7 times, and then we have 17.5 here, this occurs 5 times, and then we have 22.5 0.5 here, and this occurs one time. And if you put this into your calculator, this is equal to 300. Now, you'll notice that we are actually given this in the question, and this is quite common for exam questions to do, is to actually give you the value of sigma w and sigma w squared. The reason for this is because it kind of makes it a bit easier, a bit shorter, the question, rather than you kind of doing this massive sum here. It kind of just allows you to do the exam question more quickly. Okay, so in this case we wouldn't actually go about doing this whole thing here. We would just take this value here and sub it in. Okay, so that means that the mean is equal to sigma w, which we're told it's 300, over n, which is the number of data values, which is all of these frequencies added together. However, we're actually told that there are 34 parcels, so n is equal to 34. And if you put this into your calculator, it's equal to 8.8235. Okay, and then for part B, we need to estimate the standard deviation. Again, this would be an estimate because we're using the midpoints here, okay? So this is the formula here for the variance. So we're given the sigma w squared, so we don't need to calculate it. If we did want to calculate it or needed to, it would be these midpoints squared and then multiplied by the frequency and all of them added together. But we don't need to, so therefore the variance is equal to sigma w squared, which is 3762.5 divided by n, which is 34, and then this is minus the mean squared, and we know the mean is 8.8235, and then it's this squared. So therefore the variance is equal to, if you put this into your calculator, it's equal to 32.8076 and so forth. So therefore the standard deviation is the square root of this number here, which if you put into your calculator to 2 decimal places is 5.73. Okay, so now we're going to go through some past exam questions. If you want to have a go at any of these questions yourself, just pause the video before I go through the answer, okay? So for this question, we're told each member of a group of 27 people was timed when completing a puzzle, and the time taken, which is X minutes for each member of the group, was recorded. And for these 27 people, sigma X is equal to this, and sigma X squared is equal to this. And for the first part, we need to calculate the mean time taken to complete the puzzle. Okay, so the mean is equal to sigma x over n. So the mean is equal to sigma x, which we know is 607.5 over n, and we're told there are 27 people, so therefore n is equal to 27. If you put this into your calculator, it's equal to exactly 22.5. Okay, and then for part D, we need to calculate the standard deviation, okay? So we need to first calculate variance. So this is sigma squared is equal to, so it's going to be sigma x squared, which is this 17623.25, and this is over n, which as we've already talked about is 27, and then this is minus the mean squared, and we know the mean is 22.5, so it's this squared. And if you put this into your calculator, this is equal to 146.4629, and then so forth. So therefore the standard deviation is the square root of this 146.4629, which if you put into your calculator to 1 decimal place is 12.1. So this is the standard deviation. Okay, so for this question, we're told a company manager is investigating the time taken to complete an aptitude test, and the human resources manager produced the table below of coded times. Ignore the word coded, we're going to talk about this in the next video, it's not relevant for this question. The times for a random sample of 30 applicants. We're given this grouped frequency table here, and we're also given these values here, and we need to estimate the standard deviation of the times, okay? So if you remember the formula for variance, it is sigma, and in this case we're talking about the midpoints here, and they've given it the letter y, so this is going to be y squared over n minus sigma y over n squared, like this here. So this is the formula that we're using. So therefore the variance is going to be sigma y squared. Now we're told sigma y squared here. Ignore this part about the f. When it says f, it essentially just means it's talking about a frequency table. It's not really that important. You can kind of just ignore it. So sigma y squared here is 5675 over n, and we're told there are 30 applicants that did this, so n is equal to 30, or you could add up the frequencies here, minus, now we haven't figured out the mean, but we can figure out the mean from inputting the values here, because sigma y, we're told, is 355, and we know n is 30, and then we're going to square this entire thing here, okay? If you put this into your calculator, it's equal to 49.1388, and then so forth. So therefore, the standard deviation is going to be the square root of this 49.1388, which if you put this into a calculator to 2 decimal places, is 7.01.